Welcome to a lesson with Dr. Powell. Let's take a look at some sorting algorithms and their complexities. First, what if we want to alphabetize a list of papers? We can start by thinking of letter categories like A through M and N through Z, and splitting up the papers in here and in here. Like we go through all our papers and just put them in these two categories. We could split this into two categories, that into two categories, and then split these the same way. Then we could do this again and again until finally we have everything sorted. Now, this particular process of going about this, let's think what happens at each level. At each level, you're putting, let's suppose you have n things you're sorting. So you have n, you're putting something in a pile n times. Same thing here, you're putting something in a pile n times here if you look at every single pile, because total cumulatively you have all the papers still, or all the items at each level. So you're gonna have n per stage or per level. How many levels do you have? Well, notice what's happening. Every time you go through this, you're doubling. So from here 2 to 10, you're doubling it and so forth. So it's kind of like saying 2 to what power is going to get you roughly close to n. That's like saying log base 2 of n. So you have like log base 2 of n levels approximately, and then you have about n things per level that you're doing. So the complexity would be big O of that. Now keep in mind that we can use a change of base. So now 1 over log 2 is like a constant. So this is just the same as O log n. Okay. So in terms of log base 2 of n, so that means the overall complexity right here, which was this, could just be written as big O of n log n. And that's the complexity of this sorting algorithm. Okay, now what if we have two lists that are already sorted? What would be the complexity of merging them together? Well, we're going to use the idea that they're already sorted. So let's go through this list right here, the first list, as we come to us, okay. And what we're going to do is we're going to compare the first element of this list and see where it fits. So where does it fit here? I mean, where is it? For which ones of these is it in between? Is it before, in between, or is it after? So wherever it is, you'll insert it. And then you don't have to go back to the start list. You know, wherever you haven't even finished your traversal, maybe you're only right here. Now, how do you do the next one? You do the same thing for the next one. And then if you end up getting to the end of the list and you haven't filled them all in, then you just take the whole chunk and you just plop it at the end of the list. The effect is that you've gone through this list one time and this list one time. So the total number of steps, if you have n things and m things, would be something like n plus m. So it'd be like the big O of n plus m. Okay, so that's the complexity of a merge sort. Now, maybe for something fairly simple, how about finding the minimum of a list? How do you find the minimum value in a list? Well, you can go through your list, and you can kind of over here have current minimum. So you have you start off by just taking the first guy and putting it in here. Then you go to the next guy, and if this is smaller, then you replace it with the next guy, and you keep on going through the whole thing until when you've gone through the whole list, you'll have the actual minimum appearing here. All that's been done is one traversal, and so if n is the number of steps, the complexity would be big O of n. Thanks for watching.